So in the first part of the course, we basically looked at variable length source coding. Right? We wanted zero error. The setup was the following. We had a source sequence xn, which is distributed according to some distribution pxn. This is over some alphabet called the source alphabet. And we've so far been assuming that the source alphabet is finite. The goal is to compress this using an encoder into a k-bit binary string so that you can decode this in some way. It's assumed that at least for some part of the course, we assume that both the encoder and the decoder know the distribution Pxn. But in the last few classes, we explored the case where the distribution Pxn is not known. So prior to this, we required xn hat to be equal to xn with probability 1. So we want zero error lossless compression. But now we'll relax that particular requirement. We'll say that xn hat need not be equal to xn all the time, but it's allowed to be different with some small probability. In particular, I want the probability that xn hat is not equal to xn to go to 0 as n tends to infinity. It's something that decays as we take longer and longer length source sequences. But then we'll impose another constraint, which is that k, the length of the compressed sequence, be fixed. So k can depend on the distribution, where it is not allowed to depend on the realization of the source. Right? So in this case, we want to keep k fixed. So it can depend on Pxn, but it can't depend on the exact realization of xn. All right. And we'll define the rate r to be equal to k by n. And we want the probability of error p sub e, which is the probability that xn hat is not equal to xn. So this is some little o of 1, which means that this goes to 0 as n tends to infinity. Now when it comes to standard, say, text compression or file compression problems, this is not really what we require. Typically in such scenarios, we want perfectly zero error. But then there are other situations, for instance, when it comes to communication, where you can potentially allow a small amount of error. Because anyway, there is going to be some noise because you're going to transmit through a noisy medium. And this noisy medium is anyway going to introduce some amount of noise, so there will be some amount of error. So this additional error sometimes is not so much of a problem. All right. So that's one reason why we look at fixed length source coding. The other reason why we'll focus on fixed length source coding is not really for the solving this specific problem itself, but rather because we'll use this to develop some mathematical tools which have much wider applicability. We'll develop a set of tools which we can use to analyze lossy source coding and also subsequently channel coding. How do you communicate reliably in the presence of noise? All right. So we'll introduce those tools through this problem of fixed length source coding and then apply it to a whole bunch of other problems. And these tools are going to be very different from what we've seen previously. So previously we were very focused on algorithmic issues. We want a low complexity compression scheme. Henceforth, we'll not worry so much about the complexity. All we want are, so we have a couple of metrics. In this case, we want the rate to be as small as possible, we want the probability of error to be as small as possible, and that is the only requirement. Even if it is computationally very intensive, it is still fine. Okay. Any questions? All right, great. So now if we had to focus on this fixed length source coding problem, what do you think would be the optimal fixed length compressor? So suppose let's fix some distribution Pxn, which means I've already fixed the length of the source sequence n. This is given to us. And suppose I've also fixed k. All right. So now the only thing that is left over is the probability of error. So what do you think would be the source code, the fixed length source code, that would minimize the probability of error? What do you think that fixed length compressor would be? I'm sorry? In this case, k is fixed, so you have 2 to the k possible sequences. So k bits, right? So how do you design? How do you design the encoder? What is the decoder? You have you have size of x to the power of n possible source sequences. Okay.
So now find the number of bits by taking log.
Okay, that's some. But then, in general, we are assuming that k is something less than n times the log of cardinality of x, right? Because again, we are allowing a small amount of error. Not all of the source sequences have to be decoded correctly.
Then we know the probabilities of the sequences.
You know probabilities of all of the sequences,
so
yes.
We have k bits, we can assign unique codes to bar k of them.
Correct.
Then we assign the highest to bar k probability sequences with the correct bits, and then the lower ones will just map them to all zeros or all ones, so that doesn't matter which way.
Correct. Very good. So basically the idea is the following. You again, this goes back to our design of the optimal variable length source code. So you write down all of the sequences in decreasing order of the probabilities. All right. So let's say I have xn of 1 up to xn of size of x to the power of n. Right. Since my code word or the compressed sequence has length k, I can only represent this using k bits. I can have 2 to the k possible code words, right? No more than that. And only those code words. So basically, what is an encoder? It's basically a mapping from all of these sequences to the 2 to the k possible code words. All right. So it means that only at most 2 to the k possible source sequences can be recovered correctly. No more than those can be recovered correctly, because then at least 2 source sequences would map to the same code word sequence. All right. So we can recover at most 2 to the k possible source sequences correctly. You all agree with this point, right? So which 2 to the k possible source sequences should we represent correctly? The rest of them we can't do anything, because we are fixed by the rate. We can't represent more than 2 to the k possible source sequences. So which of those 2 to the k sequences should you choose? It should be those which have the highest probabilities. All right. So then you represent the first sequence by the all zeros code word. And so on, you assign there are 2 to the k possible sequences. You would list them in decreasing order of the probability, and you assign code words to all of to the top 2 to the k source sequences. Right? For the remaining, it doesn't matter what you assign. Right? You can assign either the all zero sequence, because anyway there is no hope of recovering these correctly. Right? So the encoder maps each of these size of x to the power of n possible source sequences to these 2 to the k code word sequences. What does the decoder do? Well, the decoder only has to see this part of this code table. Given, let's say it observes one of these code word sequences, it just decodes the corresponding source sequence in this table. That's it. So it is only these source sequences which can be recovered. The remaining source sequences can never be recovered correctly. So what is the probability of error? When does an error occur? Correct. So basically an error occurs only if you see the bottom few sequences. So this is just summation I equal to 2 to the k plus 1 up to size of x to the n of the probability of the ith source sequence listed in decreasing order of probability. Right? So this is, and you can see that this is an optimal source code, because there is no way you can achieve a probability of error that is smaller than this, precisely because this set of source sequences, the top 2 to the k source sequences, are those which have the highest probability, and therefore the bottom remaining source sequences are those which have the least amount of probability. No other collection of those many sequences has a smaller probability. That's because of the way we have chosen this set. Right? Yeah. Yes.
We are assigning them to all zeros. So
Yes, correct.
while decoding, won't the x power n of one sequence will also be an error?
No, so that's how you define the decoder, right? So if the decoder sees the all zero sequence, it is going to decode it to xn of 1. That is the rule. That's the decoding rule. Okay. So basically, if you see the all zero sequence, you will always decode it to xn of 1. You will never decode it to any of these sequences. That's why the decoding error occurs. All right. Any other questions?
It can never be said that the others are correctly decoded.
Yeah.
Never.
Never. The decoder is never going to output any of those bottom sequences. Alright. Because if you did, then it would mean that one of these sequences are decoded incorrectly, which would mean the probability of error is only higher. Okay. All right. So let's give this set a name. Let's call this, say, B KN. Right? So a set of 2 to the k sequences which have the highest probability. All right. So we know what the rate of this is, but as of now we don't have a good bound on the probability of error. What we want to know is what is the smallest k. So we're assuming that k is equal to n times r. So equivalently, what is the smallest possible r for which the probability of error goes down to 0 as n tends to infinity. Right? That's the goal. What do you think this is? It's going to be equal to the entropy. All right. Now there's one way you can try to find the probability of error for this, or try to bound the probability of error for this particular set, or this particular optimal coding scheme, but we will use a different approach. All right, and that's because that particular approach will allow us to solve many other problems. And this other approach essentially follows from the following intuition. Let's take the simplest case, which is binary. Assume that you have a Bernoulli P sequence. So henceforth we will assume that xn is memoryless. So the xn is IID Px. Okay. So let's start with the simplest case, which is the Bernoulli P sequence. So if you see a Bernoulli P sequence, what can you say about the Bernoulli P sequence as n becomes larger and larger? What's the most obvious thing you can say about this sequence? What kind of sequences are likely to occur? Or let's do something a little different. Let's say I define this set T epsilon, which is the set of all sequences where the number of ones is epsilon close to P. All right. So it's the number of sequences for which the weight of xn, which is nothing but the number of ones in xn, minus n times p is less than or equal to n times p times epsilon. Okay. What can you say about this particular set, or what can you say about the probability of this particular set?
1 if n is large.
It's not equal to 1, but something that tends to 1 as n goes to infinity. Right? All right. So one thing to keep in mind is that this T epsilon is not the set of all possible sequences with the highest probability. Because which sequence has the highest probability? If assume that P is between 0 and a half.
All zeros.
So yeah, so if P is between 0 and a half, then the all zero sequence is going to have the highest probability. Right? And that is not present in this set T epsilon. Okay, so this T epsilon is not the best possible set you can come up with. It's not the set with the sequences which have the highest probability, but it's still a high probability set. Most of the probability is present in this particular set. That's why the probability that xn is in T epsilon is never equal to 1. It's not even the highest, but still it is a rich enough class of sequences so that the probability of this set is something that is very close to 1 as n goes to infinity. All right. In fact, we can do a little more. How would you bound the probability that xn is in T epsilon? Or what is the probability that xn is not in T epsilon? How would you bound this probability? Yep, so it's a Chernoff bound. Because what can you say about this weight of xn? It's a product of zeros and ones. So in other words, the weight of xn is effectively just, what I'm asking for is something even more basic. The weight of xn is nothing but summation I equal to 1 to n xi, right? And each of these xi's is an IID Bernoulli P random variable. So it's a sum of IID Bernoulli P random variables. So you can use your favorite concentration inequality. In this case, we can use the Chernoff bound for Bernoulli P random variables. And this is less than or equal to 2 times e to the minus n p epsilon square by 3 for epsilon between 0 and 1 by the Chernoff bound. Okay, so we have a very nice bound on the probability of error for any epsilon. But what about the rate? How large can the rate be? Basically, we have to bound the number of sequences in T epsilon. So the size of T epsilon is basically the number of sequences in T epsilon, which is equal to the weight can vary from np into 1 minus epsilon all the way up to np into 1 plus epsilon. Effectively, what this is saying is that the weight of xn is between np into 1 minus epsilon to np into 1 plus epsilon. So the size of T epsilon is summation of all of these times the number of sequences with weight exactly equal to w, which is what? How many sequences are there? How many binary sequences do you have which have exactly w ones in them? It's exactly n choose w, right? That's okay. I agree it should be floor or seal, but I'm going to ignore those things for now, okay? Because it's going to just differ by, I'm going to be a little loose over here, but yeah, you're right that it's less than or equal to floor of this up to seal of this particular quantity. Okay. So out of these, which term do you think would dominate n choose w? How does n choose w grow as a function of w? We're assuming that p is something which is less than half, all right? And we'll assume that epsilon is also something that's very, very small.
It's maximized in the middle. So
It's maximized when w is equal to essentially n by 2. So we'll assume that np into 1 plus epsilon is something that's less than half. Okay? Just by assuming that p is less than half and epsilon is something very, very small. Because that's what we are interested in. We want to get as close to entropy as possible. All right? So we'll choose epsilon really, really small. think about epsilon as 10 to the minus 3 or something like that. So this is equal to, this is less than or equal to, it's a sum of these many terms. So it's less than or equal to the number of terms times the largest term, which is 2 times np epsilon. Again, I'm going to ignore the C and the floor because it's only going to, it's not going to change the order or the high level behavior of this particular quantity, times n choose np into 1 plus epsilon. Right?
How did we get and choose NP times?
Because which for what w is this quantity the largest?
N by 2.
It's n by 2, but among these quantities, it's the largest there,
Yeah.
but it is actually increasing from 0 to w by 2 and then decreases from w by 2 to n.
Because P is less than half, so the upper bound is lesser than by
The upper bound, that's why I'm assuming that the upper bound is less than half, right? This is of course assuming that np into 1 plus epsilon is, or p times 1 plus epsilon is less than half, or less than or equal to half. Which is reasonable to make because p is something between 0 and half, and epsilon is, you should think of epsilon to be something that is very close to 0. Okay. Have you seen any bounds on the binomial coefficient in terms of the entropy? Okay, so I'll leave this as I'll give this as an exercise. Basically show that this quantity is less than or equal to 2np epsilon times 2 to the n times the binary entropy of p times 1 plus epsilon into 1 plus little o of n. The basic idea is to use Stirling's approximation. All right. So this is a useful result to always keep in mind. N choose k, or n choose n alpha for alpha between 0 and half is behaves as 2 to the n times the binary entropy of alpha times 1 plus little o of 1. And we'll make use of this again and again. All right. So this quantity, let's so therefore the size of the typical set, the size of T epsilon is less than or equal to 2 to the power n times the binary entropy of P times 1 plus epsilon 1 plus little of 1 plus log of 2 np epsilon. I just wrote 2 np epsilon as log of, or 2 to the log of 2 np epsilon. But then log of some constant times n is much smaller than some constant times n. So the first term effectively dominates. So this quantity is 2 times n times the binary entropy of P times 1 plus epsilon 1 plus little of 1. Any questions? So basically I've done nothing much. I'm just counting the number of sequences for which the number of ones is epsilon close to P or epsilon close to n times P. And I'm doing this just by taking a bound on the binomial coefficient. As n becomes large, the binomial coefficient behaves effectively as 2 to the n times the binary entropy. All right. So this is, I can write this as 2 times the words. So what is the rate? It is k by n, but in this case, since T epsilon has a certain number of elements in it, how many bits do I need to represent the elements in T epsilon? Log of the cardinality of T epsilon. Okay, maybe let's go step by step. So given this T epsilon, how do I construct a compression scheme? Basically, the compression scheme works as follows. So you assign a code word for every sequence in T epsilon. So every element in T epsilon gets a distinct code word. If there's a sequence that is not in T epsilon, you assign it, let's say, the all zero sequence. So basically, only those sequences in T epsilon are going to be reconstructed, are going to be decoded correctly. Any sequence that is not in T epsilon will not be decoded correctly. All right? And since we know that the probability, so in this case, the probability of error is the probability that the source sequence is something that is not present in T epsilon, which we anyway know is upper bounded by 2 times e to the minus n p epsilon square by 3. So this goes to 0 as n tends to infinity. And the rate of this compression scheme is just log of the number of sequences in T epsilon divided by n, which is the binary entropy of P times 1 plus epsilon plus something that quantity that goes to 1 as n tends to infinity. Any questions?
So E is always lesser than 1.
Which one?
Epsilon.
Epsilon. Epsilon, you think of epsilon as something that is very close to 0. Right? Not even close to 1. Because we want sort of the best compressor possible, in the sense that we want the smallest possible rate. What we are really interested in is characterizing the smallest possible rate for which the probability of error can be made to go down to 0. All right. So the smaller epsilon is, the smaller the rate is going to be, right? Because the T epsilon will have fewer sequences if epsilon is closer to 0. And that's why we'll choose an epsilon that is very, very close to 0. Okay. But a lot of this still goes through as long as P times 1 plus epsilon is less than half. Right? So for example, if P is say 0.1, even if epsilon is 1, this at least the bound on the rate still holds. All right. Any other questions? Okay, so let's go back to see what was the high level idea behind constructing this scheme. I don't claim that this particular approach is optimal, right? Clearly it is not the one that gives the least probability of error, but it is one fixed length compressor. And later on we'll see that this is in fact not too bad. You can't do any better than this if you just want to minimize the rate. All right. So in this case, if you recall, we started with defining this particular set T epsilon, which is the set of all sequences with whose first order statistics are basically given by the probability. Since it's a Bernoulli P sequence, you would expect the number of 1s to be close to P and the number of 0s to be close to 1 minus P. Right? This is the first thing which essentially follows from the weak law of large numbers. Right? So based on this weak law of large numbers idea, we chose this particular set, and for this particular set we saw that, again, by our choice, the probability of error is something that goes to 0 as n goes to infinity. But the size of this particular set is very close to the binary entropy. In the context of zero error lossless compression, we saw that you can't do any better than entropy, effectively. Right? And in this case, I can make epsilon to be as small as I want. Right? Because as long as epsilon is greater than 0, this quantity goes to 0 as n goes to infinity. In fact, in this case, I can even choose epsilon to be something that grows very slowly with n. Right? Or in other words, decay. So for example, if I choose epsilon to be, say, 1 over log n, right? This exponent would be some constant times n over log square n, which still, and therefore this still goes to 0 as n tends to infinity. So even if I choose epsilon to be, say, 1 over log n, this quantity tends to the binary entropy as n tends to infinity. Okay, but just for convenience, we'll take epsilon to be some fixed positive constant that can be chosen to be arbitrarily close to 0. It's kind of the back off from the entropy. Okay, so that was the high level idea for the Bernoulli source. Let's see how we can generalize this to an arbitrary discrete memoryless source. So let's suppose that I have a set, so I have a PMF, Px, on some finite alphabet. So if you see an IID sequence xn, where each xi is drawn according to Px, what can you say about the frequency? What would be the first order statistics? The first order statistics would essentially be the frequency of occurrence of each symbol in the sequence. And what can you say about that? The frequencies of occurrence should approach the PMF. All right. So let us use that itself to construct our set. So let's define a few quantities. Let's say I give you a sequence xn. We'll denote the frequency of occurrence of the symbol x in the sequence xn as by mu xn. So it's the number of times x occurs in the sequence xn whole divided by n. Okay, so just some notation. Mu xn of x is the fraction of times the symbol x occurs in the sequence xn. Okay. Now, what can you say about expectation mu xn of x for an IID sequence or in any stationary sequence xn? This would be Px of x. Okay. So let us define, similar to what we did in the Bernoulli case, let us define T epsilon to be the set of all sequences for which all of these empirical frequencies are epsilon close to the corresponding probabilities. So I'll define T epsilon, let's define Tn epsilon Px to be the set of all sequences for which the frequencies of occurrence, so the fraction of times x occurs in the sequence xn minus Px of x is less than or equal to epsilon times Px of x, and this happens for all symbols x. So in the binary case, what this basically says is that the number of zeros is close to 1 minus p and the number of ones is close to p. So this is called, we'll define this as the epsilon typical set. And this particular quantity mu xn, which is the set of empirical frequencies of symbols in the sequence xn, we'll call this the type of xn. All right. And in fact, any PMF of the form n1 by n up to n size of x by n. So any PMF where the probabilities are ratios of two natural numbers, where the denominator is always n. So this PMF will be called type. More specifically, we'll call it an n type because the denominator is equal to n. Alright. So basically, if you have a sequence of length n, then the corresponding type will be an n type. Okay. Just some terminology. There's nothing substantially new that I'm saying over here. I'm just establishing some notation that will make it easy for so on. So basically this T epsilon, the epsilon typical set, is the set where the type of xn is close to the true probability. And it's close to the true probability. In fact, in terms of, loosely speaking, the L infinity distance. Not exactly, but yeah. So each component of mu xn is close to px of x by an amount epsilon times px of x. Okay? Any questions? Okay, great. So one other thing that maybe an additional assumption that we'll make. So we'll assume that xn is IID px and all symbols have positive probability. Otherwise, we can just remove it from the alphabet. Right? This is an assumption that we've been making throughout, but I'd still like to point it out. Okay. So why is the epsilon typical set important for us? In the context of fixed length source compression, we'll assign unique code words to only those sequences which are going to be in the epsilon typical set. If it's not in the epsilon typical set, then we'll assign it the zero code word. Okay? So these are the sequences which will be decoded correctly. And our hope is that the epsilon typical set has almost the smallest possible size. At least in the first order in the exponent, this is the smallest possible. All right, so the compressor basically you assign unique code words to sequences in Tn epsilon of px. Again, keep in mind that n and px are fixed. They're known to us, both the encoder and the decoder beforehand. So we first design the entire code based on n comma px. All right, and then you assign the all zero sequence to sequences which are not in the typical set T n epsilon. So every sequence in T epsilon n epsilon will be decoded correctly. Every sequence that is not in T n epsilon will be decoded incorrectly. All right. So the probability of error is the probability that the random source sequence happens to be outside T n epsilon. And the rate is basically, what is it equal to?
log to cardinality of.
Right, so it's 1 over n times log cardinality of T n epsilon. Any questions? Okay, so therefore now we need to do two things. One, we have to find the probability that a random source sequence does not lie in T n epsilon. The second, we need to bound the size of T n epsilon. All right. Let's do the easier thing first, which is the probability that xn is not in T n epsilon. How would you bound this particular probability?
Union bound less than union bound.
Okay, can you elaborate on that? What would be the approach?
Probability of xn not being there is
Correct.
equal to summation of
Huh.
probabilities of individual x
Huh.
i's not being there. The earlier t just for one symbol.
Okay, so basically what you're trying to say is the following. So the probability. So recall that for a particular sequence to be in T n epsilon, all of the empirical frequencies should be epsilon close to px. So if a sequence does not lie in T epsilon n epsilon, then it must mean that at least one of the empirical frequencies is not epsilon close to px. Do you agree with this part? Any questions? Great. Now, this particular event that mu xn is not epsilon close to px is basically a union of events. So this is the probability of a union x in x correct? So I can then use a union bound to write this as less than or equal to summation over all x in x, probability that mu xn of x right. Now how would I bound this particular probability? Why go for Markov? You can use Chernoff, right? What is mu xn? Mu xn is essentially a sum of indicator random variables. Right, so each of these, it can be written as an average of indicator random variables. So each of these is a Bernoulli Px of x random variable. Right, what is the expectation of this particular random variable? It is the probability that xi is equal to x, which is just Px of x. So just using Chernoff, this is less than or equal to summation over all possible x e to the power 2 times e to the power minus n Px of x epsilon square divided by 3. Again, keep in mind that epsilon is something that's very small, much smaller than 1. So this bound can be used directly. This holds true for all epsilon less than 1. All right. So clearly, since the alphabet size is finite, and each of these terms goes to 0 as n tends to infinity, this whole quantity goes to 0 as n tends to infinity for any epsilon greater than 0. If you want a cleaner bound on this quantity, you can upper bound this by the number of terms times the largest possible term, which is e to the power minus n times the smallest probability times epsilon square divided by 3. All right. Where P min is the min over all x of Px of x. And we're assuming that this quantity is strictly greater than 0. That's one of the reasons why I assume that all of the probabilities are greater than 0. If not, I just have to handle them separately. It just becomes inconvenient more than anything else. Nothing breaks down. Okay. So if I encode sequences, only those sequences that are there in the typical set, then the probability of error will go to 0. That is guaranteed. So now let's try to, what we want to do is how large can the rate be? And is this really optimal? Right? That is something we've not resolved yet. It's clearly not the best. It's not that compressor which minimizes the rate, but we'll see that in fact it asymptotically minimizes the rate. Asymptotically, you cannot achieve a rate that is any less than this. So now we want to bound the rate, or in other words, we want a bound on the size of this particular typical set. We'll go a step further. We'll try to understand various other properties of the typical set. So first here we'll show a very general result. So let's take any function g defined on x. Okay, it could be your favorite function. And you take any sequence in the typical set. Pick any sequence in the typical set. Doesn't matter which sequence you pick from the typical set. All right? Then it has the property that if you take the average of g, the empirical average of the g of xi's, it turns out that it is going to be very close to the expectation of g of xi. So the typical set has the following property that for any sequence in the typical set, the empirical average of any function of this particular sequence is going to be close to the corresponding expectation with respect to the true distribution Px. And to see why this is the case, it's very simple. So 1 over n times if you take the empirical average, you can rewrite this in the following way. It is just sum over all possible x g of x times the number of times the, or if I take, so if I take g of x times the number of times the symbol x occurs in the sequence xn. It's just rewriting the summation in a different form, which is nothing but 1 over n summation over all possible x g of x times n times mu xn of x. Because remember, mu xn is the fraction of times each the symbol x occurs in the sequence xn. So it's the type of xn. But you know that mu is within 1 plus or minus epsilon of px. So this quantity is less than or equal to summation over all x g of x times 1 plus epsilon px of x. It is also less than or equal to, and it's greater than or equal to 1 minus epsilon times 1 plus px of x. But then what is this? If I take the 1 plus epsilon outside, what is the remaining quantity? It's just expectation of g of x. Right, so that's straightforward. So let's take a very specific choice of G. We take this to be log 1 over px of x. Okay. Then what do we get? So 1 over n summation I equal to 1 to n log 1 over px of xi. What is expected value of g of x? It's equal to the entropy, right? So this is less than or equal to 1 plus epsilon times the entropy, and greater than or equal to 1 minus epsilon times the entropy. Okay, but that's not what is remarkable. Let's look at the quantity in between. I have 1 over n summation I equal to 1 to n log 1 over px of xi, which is 1 over n log 1 over the product I equal to 1 to n px of xi, right? This is nothing but 1 over n log 1 over the probability that xn is equal to little xn. Okay, remember this is only for a sequence xn in the typical set, only for those sequences. This in general will not hold for sequences outside the typical set. This is what we call a typical sequence. Okay, so this quantity, what we've shown, is less than or equal to 1 plus epsilon times the entropy. It's greater than or equal to 1 minus epsilon times the entropy. So if I look at the probability that xn is equal to xn, which is pxn of xn, this is less than or equal to 2 to the negative, again just by taking n to both sides, taking the exponent and inverting, this is less than or equal to 2 to the minus n times the entropy times 1 minus epsilon. It's greater than or equal to two to the n times minus n times the entropy times 1 plus epsilon. So this tells us that there's something special about those sequences in the typical set. So for every sequence in the typical set, the probability of occurrence of that one particular sequence is very close to 2 to the minus n times the entropy. All right? We'll see why this is important in a little bit. Now, so we have this. The next point is, how do we bound the size of the typical set? Okay. For this, we'll play a trick, which is, what is the probability that xn lies in the typical set? This quantity is nothing but summation over all possible xn in the typical set of the probability of occurrence of that particular sequence. Okay. Now this quantity, okay, well, let's do two things. First, we'll derive an upper bound on the size of the typical set, and then we'll derive a lower bound. For the upper bound, now this quantity is a probability, right? And how large can probability be? It can be at most 1, right? So this quantity can be at most 1. This quantity is at most 1. And we also know that the probability of any sequence in the typical set is at least 2 to the minus n times the entropy times 1 plus epsilon. So I'll use this particular lower bound to lower bound this particular quantity. So summation xn in the typical set of 2 to the minus n times the entropy times 1 plus epsilon is less than or equal to 1. All right. Now this quantity no more depends on xn. I can take it outside the summation. So this is basically the number of terms in the summation times this particular quantity. But how many terms are there in the summation? The cardinality of the typical set. Which means that the cardinality of the typical set is less than or equal to 2 to the power minus or 2 to the plus n times the entropy of x times 1 plus epsilon. All right, any questions? Okay, so let's derive a similar lower bound. Now, to derive this upper bound, what did we do? We use the fact that the probability that xn is in the typical set is less than or equal to 1. To prove a corresponding lower bound using the same approach, all we need is a corresponding lower bound on this quantity. What is the lower bound that we can use? What do we know about this particular probability? As n tends to infinity, what can you say about this quantity? It goes to 1, right? Because we've shown that the probability that xn is not in the typical set goes to 0 exponentially fast. All right. So or basically the probability that xn belongs to the typical set, this is exactly equal to 1 minus the probability of error, right, which we showed decays exponentially fast. So more precisely, if we use the same approach, this is equal to 1 minus the probability of error, which is a 1 minus little of 1. But this quantity is greater than or equal to two to the minus n times the entropy times 1 minus epsilon. So here I am essentially using this upper bound on the probability that xn is equal to xn. So this quantity is greater than or equal to 1 minus the probability of error, which is 1 minus something that goes to 0. Right? So the size of the typical set is greater than or equal to 1 minus a little of 1 times 2 to the n times the entropy times 1 minus epsilon. And we have also shown that this is less than or equal to 2 to the n times the entropy times 1 plus epsilon. So the size of the typical set is close to 2 to the n times h of x, right? And so the number of sequences is roughly 2 to the n times h of x, close to 2 to the n times h of x. And what we've also seen is that the probability of each of these sequences is also approximately the same, roughly 2 to the minus n times h of x. which means that within the typical set, all of the sequences are almost uniformly distributed. All of them have roughly the same probability, right? Same probability up to a 1 plus minus epsilon in the exponent. All right. So, and that is intuitively why compressing only the typical set can be a benefit. So within the typical set, it's a set of sequences which all have almost a uniform distribution. It's a high probability set, and all of the sequences within this set have an almost uniform distribution. And you're assigning each of them a fixed length code word. All right? Which means that if you look at the compressed sequence, all right, every compressed sequence is almost equally likely. Correct? So basically the probability that Ck is some particular sequence is very close to 2 to the minus n times h of x times some function of some delta of epsilon. But this delta is very close to 0 as epsilon becomes very close to 0. So the compressed sequence is almost uniform, which is good because if it were not uniform, then it means it can be compressed even further, right? So this tells you that the compressed sequence is not really compressible any further, which intuitively suggests that this compression scheme may be optimal. The additional factor you require is that the probability of error should be close to 0. Otherwise, it's not a good compressor, right? Okay, so now that we have this, what is the rate? So the rate is 1 over n log cardinality of Tn epsilon of Px, which again from the bounds that we have, this quantity is less than or equal to entropy times 1 plus epsilon, and it is greater than or equal to entropy into 1 minus epsilon plus a little of 1. Right, so just as in the binary case, we see that the rate is very close to the entropy. So there are a couple of reasons, intuitive reasons, as to why this could be an optimal compressor. For one, just the argument that I gave, that the compressed sequence is almost uniform and it's not further compressible. The second goes back to one of the questions that you had in the first exam. That is, if you have a fixed length compression scheme of some rate, then you can actually convert that into a variable length compression scheme of effectively the same rate as long as the probability of error is vanishingly small. Right? And the way you do it is the following. So you can use this to come up with a variable length compression scheme, which is if the sequence that you observe lies in the sequence that you're in the set that you're compressing, then you assign the NR length code word. If xn is not in Tn epsilon, then you assign the n times the actual binary representation, the uncompressed binary representation. The expected length would be equal to nr times the probability that xn is in the typical set. So with probability equal to this, you assign an nr length code word, and with some very small probability, you assign an n length code word. So this is essentially n times r plus little o of 1. So it has the same rate asymptotically, but it has zero error, right? Because all of the code words that in the fixed length compression scheme, where you assigned, where you are actually incurring an error in the fixed length compression scheme, you are going to send those in uncompressed form. So given any fixed length compression scheme, you can convert it to a zero error variable length compression scheme by paying a very negligible overhead in terms of the rate. So this negligible overhead is something that goes to zero as n tends to infinity. All right. So what is the rate of this variable length compression scheme? Defined using the typical set. It's R. And in this case, what is R? It's equal to entropy, right? So if for fixed length compression, if I could do better than entropy, then it must mean that I should be able to do better than entropy for variable length compression, which we know is impossible, right? So it means you can't really beat entropy even for fixed length compression. That is indeed the best possible rate. All right. We'll see another proof for why the entropy is the best possible that we can achieve for fixed length compression scheme in the next class.